this one small one. Hello, am I audible? Okay, I guess I am. Okay, so today we'll solve some problems related to week number 7 of quantum mechanics and molecular spectroscopy. So coming to the first question, calculate the ratio n1 over n0 of molecules in n equal to 1 and n equal to 0 vibrational states for carbon monoxide at 25 degrees Celsius, and assume it's a harmonic oscillator with frequency this much. Okay, so what we have to calculate? We have to calculate the ratio n1 over n0. That means number of particles or number of particles in n1 state divided by number of particles in n0 state. So this is n0, this is n equal to 1. Okay, so we can we know like as we are assuming this is a harmonic oscillator, so we know the energy. This will be n plus half h cross omega, right? Now this is given in terms of centimeter inverse. Let me denote the energy related with respect to this wave number g tilde. Then this will be n plus half n tilde. Okay, this is just different notation. Okay, so we know the energy formula. Now we can calculate the energy difference between these two states. Okay, so this energy difference delta E, we can write G1 tilde minus G0 tilde, right? So this will be nu E tilde, n is equal to 1 here, so this is one plus half minus n E tilde, n equal to 0 here, so 0 plus half. So this will effectively give me nu E tilde, right? So delta E is nothing but nu E tilde. Okay, now we know from Boltzmann population distribution, this n1 over n0, this will be equal to e to the power minus delta E over kt, right? Then, or if there is some degeneracy, this will come as 2j plus 1 here multiplied with this. Okay, so as we for our case, okay, this is different, so j won't come here, so let's not write j. Okay, so from Boltzmann distribution formula we can write n1 over n0 to be e to the minus delta E over KT. And KT for 25 degrees Celsius is already given in terms of length inverse. So it's very pretty straightforward now. Delta E we have already which is this much, and KT is also given. So this is 2169.8 207.2. Okay, so this will give us, just put it in calculator, so you will get around 2.83 times 10 to the power minus 5. So what we see, N1 is 2.83 times 10 to the power minus 5 into N2. So what does this mean? This means there are very few particles in this N1 state compared to N0 state. Okay, at this temperature. Any doubt? Hello? Okay. Moving on to the next question then. Okay, it's similar. Now we have to calculate N1 over N0 for molecule in J equal to 1 and J equal to 0 rotational levels for carbon monoxide molecule at the same temperature. And the constant Regulator constant is given to be this much. Okay, so for like we know, for rotational states, if J is non-zero, then there will be 2J plus 1 degenerate states similar to ml. Okay, so the energy in terms of this rigid rotor constant and J, we know is to be, let's denote it to be Fj, then this is Be tilde J times J plus 1. Okay, so as for J equal to 0, if you put J equal to 0, this F of 0 will give us 0, right? So the energy difference between J equal to 0 and J equal to 1, let's denote it to be delta E. F, okay, this is 1, F1 tilde minus F0 tilde. This will give me this B tilde. This is 1, so 1 times 2 is 2 B tilde, right? So this is in terms of wave number. Okay, as it is given in terms of centimeter inverse, so it's in terms of wave number. Okay, now for any single rotational state with J equal to 1, this N1 divided by N0 according to Boltzmann distribution, it can be written as e to the minus delta E over KT. Okay, so this will give us e to the power minus, this is one second. Okay, yeah, 2B is okay, 2 and B is 1.932 centimeter inverse. So KT is also given 207.2 centimeter inverse. So if you solve this, you will get the number 0.9815. Now this is the population in every state. Like for j equal to 1 state, there will be some degeneracy, right? So there will be 2j plus 1 degenerate states. Okay, so if j equal to 1, then there will be 2 into 1 plus 1, 3 degenerate states. Right, so mj, this is -1, 0 or 1. Okay, so in each state there will be this much fraction of particles. Let's say n1 will be 0.9815 times n0. So in each state there will be this much fraction of particles. So there are total particles in n1 state, therefore will be n1 by n0 equal to 2j plus 1 to the minus delta E over kt. Right, so this is nothing but 3 times 0.9815. okay, so this will give us 2.945. so as the states are degenerate, so the number of particles in the excited state will be more compared to for ground state. Or let's say the number of particles in excited state will be more for j equal to 1 compared to j equal to 0 state. Okay, so number of molecules in j equal to 1 state will be more compared to j equal to 0 state. Okay, this is due to degeneracy of state. If j is more than 0, then there will be degenerate states. So in each degenerate state, each state hold same energy, right? So they can accommodate same number of particles. So if j is non-zero, then it can accommodate more number of particles compared to j equal to 0 state. Okay, any doubts? So let me repeat the question. So we had to calculate this ratio n1 over n0 for molecules in j equal to 1 and j equal to 0 rotational levels for this carbon monoxide molecule at temperature 25 degrees Celsius. Okay, and assuming rigid rotor approximation, B is also given and kt is also given. Okay, so in rigid rotor approximation, we can calculate the energy in terms of this rigid rotor constant as this. So the energy difference between j equal to 1 and j equal to 0 state will be giving us 2 dE, which is all this. Okay, then using Boltzmann distribution law, this n1 over n0 will be e to the minus delta E over kt. Okay, and delta E we already calculated. This is 2 BE tilde divided by kt. So this ratio is giving us this one. So this much fraction of molecules are in j equal to 1 state compared to j equal to 0. That means here. You see, so this much fraction of particles are there in one state compared to 0 state. Okay, but if J is non-zero, then there will be some degeneracy in the states. That means what? This degeneracy is 2J plus 1. So if J equal to 1, then there will be 3 degenerate states. So what does this mean? These 3 states, they will have equal energy. So degeneracy means what? So if degeneracy is 3, then these 3 states, they will have equal energy. So it's equally probable that those particles will be in any of the 3 states. Okay, so if we calculate finally the number of particles in excited state, this will give us, okay, this is not the ratio, this gives 3. This is 2J plus 1, this is effective formula, 2J plus 1 e to the minus delta E over kT. This will give us this fraction. So the number of molecules in J equal to 1 state is greater compared to J equal to 0 state. Okay, this is due to degeneration. So any doubts? Okay, so I assume no doubts. Okay, moving on to the next question. So the lowest energy transition in the rotational spectrum of HF are 41.105 and 82.211 centimeter inverse. Then calculate the equilibrium bond length for HF molecule. Okay, so what is this molecule? Hydrogen and fluorine, hydrogen fluoride molecule. So what is given? The lowest energy transition in the rotational spectrum of HF are given 40. Okay, in terms of wave number it is given. Okay, so from the previous question, what we found, the energy difference will be 2 beta tilde. Okay, sorry, 2 b tilde. We calculated here. If we consider the ground state to be J equal to 0 and the excited state to be J equal to 1, then the energy difference will be 2b. Okay, so this energy difference, this will be 2b. Okay, now the wave number in ground state, let's say this mu E1 is given this much, and the wave number in okay, so let's 0 in excited state is given this much. Okay, so this is okay, okay, this is energy. Okay, so this is given energy in terms of length inverse. So this is energy, E1 in terms of, okay, in terms of wave number is given. So delta E is E1 minus E0, which is 82.211 minus 41.105. So this will give me how much? 51.106 centimeter inverse. So this will be equal to 2 b tilde, right? So from this we can get b tilde to be 41.106 over 2, which will give me 20.553 centimeter inverse. Okay, so it's given the lowest energy transition in rotational spectrum are this. So E0 is this much in terms of length inverse, and E1 is this much in terms of length. And we know the energy difference in each state will be 2 beta tilde. Actually, this is comes with j into j plus 1, I guess, or j plus 1 from the class you might remember. So we are for initially we are considering j equal to 0, so this will give us 2 b tilde, means the difference is 2 b tilde we calculated from the previous question. Okay, so we have equated this energy difference to 2 b tilde, and from that we got b tilde. Okay, so we need to calculate what? The bond length, right? So we know b tilde. How we will proceed from here? Do you know any relation of bond length and whatever variables are given in this question? Like we did last class, or last to last class we did like this. The moment of inertia will be equal to mu r naught square. So what is mu here? This is reduced mass, and this is the bond length, right? And this is moment of inertia, right? So what we need now? We need reduced mass and a moment of inertia. What is given? B tilde is given, right? So B tilde is given, that means what? From that we can calculate the moment of inertia from this formula h naught over 4 pi b tilde c, right? Do you remember this formula? We have used this last class or before last class also, so you can check from the class. Okay, so if b tilde is given, now we can calculate moment of inertia. Okay, so h cross is what? H over 2 pi, now 4 pi b tilde c. Okay, this is h over 8 pi square b tilde c. So if you put all the values in here, so I am not doing the calculation explicitly, you can check it, or and you can verify it. This will give us 1.36 times 10 minus 47 kg meter square. Okay, so moment of inertia is given this much. Okay, so now we can apply this formula. I is mu r naught square, so which will give us r naught to be I over mu root over. Okay, okay, now we need mu also. So reduced mass formula, what is it? Anyone?
M1 M2 by M1 plus.
Yeah, m1 m2 by m1 plus m2, right? So now what is the molecule? Hydrogen fluoride. So at mass of hydrogen, mass of fluoride divided by mass of hydrogen plus mass of fluoride. Okay, so this will give us in atomic mass unit, this is 1.007825 times 18.99843 divided by this 0.07 plus 15. or you can approximately take it to be 1 times 19 divided by 1 plus 19. So this will give us in terms of atomic mass unit, right? Now you need to convert this mass from atomic mass unit to kg. So you have to multiply one constant with it, which will convert this to kg atomic mass unit inverse. So this will give us finally 1.58922 9 times 10 to the power minus 27 kg, right? So mu already mu we got, we have I from here, so it's pretty easy now. So R naught will be I over mu, this will be 1.36 10 to the power minus 47 1.58922 10 to the power minus 27 root of. So if you do this, you will get this value to be 9.25 10 to the power minus 11 meter, or you can write it to be 0.9257 Armstrong. Okay, so any doubts?
No, sir.
Okay. Okay, then we will move to the next question. Okay. Okay, two adjacent lines in the rotational absorption spectrum of this N and H molecules are at this 98.036 and 130.714 centimeter inverse. So what is given? Energy of each level is given. Then calculate the equilibrium bond length of NH. That means you have to calculate R0 and the rotational quantum number of the lowest of the lower state of the two transitions. Okay, so there are two levels are given with energy 98.036 130.714 centimeter inverse. Okay, now we know on this energy difference, let it be into let's denote it to be F, or you can write delta E. So this is not a the state j equal to 0, and this is not the state j equal to 1. It's some state which is given with energy in terms of length inverse to be 98.036 and 130.714. Okay, so these are adjacent lines. Okay, so the energy difference between these two states, let's say this is j equal to j prime double prime, and this is j double prime plus 1. Okay, so the energy difference between these two states will be j double prime plus 1 and f tilde j double prime. Okay, so in previous question I told you that the energy difference between the adjacent states, this is 2 beta tilde j double prime plus, like, as there was this j, initial j was 0, that's why this was giving us 1 in those questions. Now we don't know the value of j. Okay, that's why we are writing it in terms of general form. Okay, so this energy is given to be this much, and this energy is given to be this much. Okay, so this is energy difference. This will be then difference between these two. One second. Okay, sorry. Okay, so mm, okay, this is actually the energy difference which is needed to excite the molecule from its ground state to this state. That means this is delta F for this state. Okay, let me denote. Sorry for the confusion. Okay, so what is this? This is the energy required to excite the state from its previous state to this state. Okay, so let's write this. Okay. So if a molecule is initially in J double prime state and it is exciting to J double prime plus 1 state, then the energy required to do this transition is delta F. Okay, and this delta F formula is given in this form. Okay, so there are two scenarios, like there are two adjacent lines, like this is nothing but this delta F value. Okay, this is 98.036 centimeter inverse. Okay, this much energy is required or emitted when this transition is happening from J double prime to J double prime plus 1, and one more line is there which is some, let's say, J prime to J prime plus 1 transition is happening. They have to after so this much energy is required to make this transition from J prime to J prime plus 1. Okay, so this is the energy difference which is okay. Now one value is given to be 98.306, so we can equate this this energy difference is 98 6 centimeter inverse. So this is nothing but 2 b tilde J double prime plus 1. Okay, so p value you need to calculate, right? P value is not given. Okay, sorry for the confusion. Okay, so we did already this in previous question, right? So there were two states. Let's say this is J double prime and J double prime plus 1 state. So that the energy required to make the transition between these two states were 2 beta tilde. So in this case J double prime was 0, that's why it was 2 beta tilde. If it is not 0, this will give us J double prime plus 1. So this much energy is required to make this transition. Okay, so similarly in this case also, okay, this energy transition value will be 2 beta tilde J double prime plus 1. Okay, so these are the individual energy levels. Okay, so this is 98.036 centimeter inverse and this is 130.714 centimeter inverse. Okay, so this difference will give us this energy difference. Okay, so this 2 beta tilde will give us value the difference between these two. So this 130, just give me a second. Okay, my system is hanging. Just give me a second. Okay, sorry about that. Okay, so the energy difference between these two states will give us uh, the energy difference between these two states will give us b 2b tilde. Okay, now let's assume this for this kind of system, this is let's say j equal to 0 and j equal to 1. Let's assume like this is j equal to 0 and j equal to 1. In this case, this will give us 2 beta tilde like j equal to 0, like the energy difference, which the formula is okay. So let's assume in some system of some reference, this is our ground state and this is our first excited state. So in this case, this 2 b tilde j plus 1 will be converted to 2 b tilde. Okay, so in this case 2 b tilde will be the energy difference between these two states. Okay, 130.14 minus 98.036. Okay, so this will give us 16 point sorry, this will give us 32.5 something. Okay, and this b tilde will give us 16.339. Okay, so we don't know what is this first state and second state. So what we assume, so the first state we have assumed to be j equal to 0 and the excited state we are assumed to be first state in some j frame. Okay, now by assuming this, we are simplifying this problem. Like if we assume j equal to 0, then this difference will be simply 2 beta tilde. Okay, so from that I can simply calculate beta tilde. Okay, now coming to some different frame, let's say j prime frame, where j double prime equal to 0 is somewhere else. Okay, so assuming this frame, we calculated b tilde. Now we are going to different frame to calculate these absolute values of j. Okay, so from class you know that energy difference between two adjacent sides will always be 2 b tilde. Okay, and j plus 1. Okay, it will depend on previous states j. So if we assume this j to be 0 initially in this j frame, then it will simplify to simply 2 b tilde. Then we can easily calculate b tilde, right? Now we got b tilde to be this much. Now we can put this value here, means now we know this is the energy of this state. That means it has to be the molecule to come to this state, it has to be coming from some j double prime minus 1 state, right? So to make this transition, let's say in this case this is j double prime now and this is j double prime plus 1 state. Okay, so in this case we can directly calculate the value of j double prime from this formula. How? So in this case, what if let's assume this energy of this state, if previous state to be 0, the energy required for this transition to be going to this state is 98.036. I know it's pretty confusing to you because I messed up somehow, so sorry about that. If you don't understand it, just stop me, then we will discuss. Okay, so I can simplify this case like the energy of this state is 98.036. okay, I can imagine this scenario as this much energy is required to make a transition from its previous state to this state. Okay, so in this case delta E is this much. Okay, and for every case this B tilde is same, right? Now if I equate these two, now what will happen? B tilde we got already 2 times 16.339 times J double prime plus 1 will give us 98.036. So J double prime plus 1 will be 98.036 by 2 times 16.339, then J double prime will be this value plus 1. So if you solve this, you will get J double prime value to be 2. Okay, so this scenario, let's go here. Now assume this is the scenario like 98.306. This is the energy difference is required to make transition from this one to this one. Like we are using this formula, right? This is general formula for transition from J double prime to J double prime plus 1, right? So if I take J double prime minus 1 here and apply the same formula, it will be wrong, right? So I am rephrasing this scenario in this frame. Okay, so initial state is J double prime and the final state is J double prime plus 1, and the energy difference between these two states, let's assume it to be 98.036. okay, so I rephrased this situation, the scenario, to this form. Okay, so what was there initially? There were two states with energies 98.036 and 130.714. okay, so for that we have a formula 2 beta tilde J double prime plus 1. okay, the transition to happen, we have this formula. Okay, so we assumed what? This initial state to be 0 to get the value of beta. Okay, so then we got beta tilde value. Now we need to calculate this the transition formula. Like we don't know what is the value of J for this line and what is the value of J for this line. Okay, now this 98.036 I can rephrase this problem like this. So let's say initial state was J double prime and final state is J double prime plus 1, and the energy difference between these two transitions will be 98.036. okay, now then we have this relation, right? So then we applied this relation Now we got j prime value to be this will be equal to 3, then 3 minus 1 will give us 2. So what is this? Then this will be 2, then this will be 3. So what is this transition? 2 to 3. So 2 to 3 transition will give this transition, in this transition this much energy is released or absorbed, whatever. So this is the energy difference between these two states. If we solve this, we are getting j double prime to be 2. So j double prime plus 1 will be 3, right? So this is this much of energy, or in terms of length, in terms of wave number, this much of energy will be absorbed for transition from 2 to 3. Okay, I know it's pretty confusing. I messed up so many things. So any doubts so far? Hello? Okay, so maybe you understood everything or you didn't understand anything. Okay.
Simply transition and energy change.
Yeah.
The complex one.
Okay. Okay, so I guess you understood. Like I rephrased the problem many times. Like initially we don't know the value of j, so we made a simple assumption like initial state to be j0 and final state to be j1. Okay, so then the energy difference between these two states will be simply the difference between these two energies. Okay, then as we have assumed j to be 0, this difference will be 2 beta tilde. Sorry, I'm always saying b to be beta, 2 b tilde. Okay, so 2 b tilde will be the difference between these two values. Okay, now from that we can get b tilde, right? So we got b tilde. Now we can tackle this problem in its absolute frame. Okay, so the energy difference between any two states can be given by this formula 2b tilde j double prime plus 1, right? Now we don't know the value of j double prime. We want to calculate this j double prime. Now let's assume this j double prime has a previous line j double prime minus 1. So this much energy is required to make the transition from its previous state to this state. Okay, now I am rephrasing this problem like this. I am saying the previous state was j double prime and the current state is j double prime plus 1. Why am I doing this? I am doing this to be consistent with the formula. Like this formula is for transition from j double prime state to j double prime plus 1 state. But the initial state was j double prime and final state is j double prime plus 1. So if the initial state is j double prime minus 1 and the final state is j double prime, so in that scenario maybe this formula would look different. That's why I just rephrased the states. Okay, so the initial state I told to be j double prime and the final state I told to be j double prime plus 1, and the energy released by this transition is this much. Now I equated both the sides and then I got the value of j double prime. Okay, so I got j double prime to be 2 that means what? This transition is from 2 to 3. So this 2 to 3 transition is releasing 98.036 centimeters in this line. Okay, similarly next one also we can do 2b tilde j double prime plus 1 equal to 130.714 centimeters. So with b tilde we know, then if we solve this, j double prime plus 1 will give us 130.714 2 times 16.339. So if you solve this, this will give approximately 4. Then j double prime will be 3. So for this line, the transition is happening from j double prime equal to 3 to j double prime plus 1 state equal to 4. Right. So this line 130.714 centimeter inverse, this is releasing. This is releasing from the transition from third state to fourth state, and this line is releasing 98.036 centimeter inverse line by this transition from 2 to 3 state. Okay. So sorry, it was very confusing initially. Yeah. So you understood, right?
No, it's not a confusion.
So okay.
Actually,
Yeah, but I got confused initially, so I messed up somehow. But you understood.
actually, I had a question also that data is insufficient because we are not about J.
Yeah.
Data is insufficient. Okay, sir. Please good way.
Yeah. So initially we assume j equal to, means, so the energy difference will be same for rotational spectrum, right? So we can assume this initial to be 0 first, then we'll get 2b tilde, and it will give us the energy difference. From that we can calculate b tilde. Now we can apply this formula 2b tilde times j double prime plus 1 to be this transition line length. Okay. So
Yes.
okay. Then moving on to the next question. Okay, calculate the moment of inertia of water about z axis, which is the figure axis. Then the rotational constant about the z axis is given this much. Assume that the bond angle is 104.48 degrees. Then calculate the bond length between oxygen and hydrogen bond. Okay. So we have water molecule. Okay. So it will have one oxygen and two hydrogen atoms. Right. And saying it is oriented around z axis. Let's say this is z axis, which is the figure axis. Now the rotational so this molecule is rotating around this z axis, and rotational constant a tilde is given to be 14.512 centimeter inverse, and the bond angle is given. So this angle is given, this is, let's say, theta. This is given to be 1.0 sorry 104.48 degrees. Now we need to calculate the bond length between oxygen and hydrogen. We need to calculate. Okay, so you understood the question. We are given a water molecule which is oriented around z-axis, and the rotational constant around z-axis is given, and the angle is also given to be 104. It's bond angle between this oxygen and hydrogen molecules. It's given 148 degrees. Now we have to calculate the bond length. So any idea how to proceed?
Here, what is the relation with theta to another?
We will see. Okay, well, let me do this. So this is z-axis. So we can assume perpendicular to this axis. Let's say this is x-axis. Okay. So if it is theta, then this will be theta over 2. This will be theta over 2. Right. Then if it is bond length is ROH, then can we write this length in terms of ROH? It's just simple trigonometry. This will be then ROH sine theta over 2, right? Like if you have a right angle triangle, if this is theta and hypotenuse is some value, say r, then this axis will be r cos theta and this axis will be r sin theta, right? So adjacent side means bond length we are denoting as ROH. So in terms of ROH we can write this length in terms of ROH and bond length to be like this, ROH sin theta over 2, right? So this total length will be 2 ROH sin theta over 2. Okay, so what it becomes effectively? It becomes some molecule with some effective mass. Let's say this was m1 effective mass, and it's now rotating around this z-axis. Now this distance is 2 ROH sin theta 1. That means the bond length is now this much. Now it's effectively a diatomic system, and effect of this oxygen molecule won't be there because it's aligned with the z-axis, so it won't rotate, its position won't change by this rotation, but the position of these hydrogen molecules will change, right? So what you did, this triatomic molecule equivalently we can write as diatomic molecule, where the bond length will be 2 ROH sin theta over 2. Okay, so if we can write this triatomic molecule in terms of this approximate diatomic molecule, now what we can do, if you have a diatomic system and we want to consider its rotational motion, what we have to calculate then? Its moment of inertia, right? Along the z-axis we can calculate its moment of inertia. So as this is triatomic molecule, this total moment of inertia around the z axis will be total mass, sorry, not total mass, individual mass times individual coordinate square. Like we had I equal to mu r naught square, right? So mu, what is mu? Reduced mass. This was reduced mass, but it's mass, right? In this case also this is mass. Like in physics, if there are two mass and the distance is known, then the moment of inertia is nothing but mass times the radius square. Okay, so if you have some shape and you have some molecules in each position and you want to calculate moment of inertia around some axis, then the moment of inertia around that axis can be written as sum of all the masses times the radius square from the point. Let's say this is the reference point and there is a mass here and this is Ri, let's say the distance, this is Mi, let's say Mi. Then the moment of inertia of this kind of body will be sum of all possible masses times the radius from this origin. Okay, let's say there is a mass Mi here, so the moment of inertia contribution due to this mass at this point will be Mi Ri square. So similarly there will be some other mass at some other point, right? So the total moment of inertia will be sum of all the molecules in the system, right? If it is a stone and you want to calculate its moment of inertia, so you have to consider all the particles distributed in the stone and its relative position from the point of reference. Like you want to calculate moment of inertia with respect to some axis, right? So from that axis, how much distance the particle is and what is the mass of the particle. So the total moment of inertia will be coming from all the masses and their distances from the reference axis. Okay, so in this system also we have three atoms, three particles. So the total moment of inertia around this z axis will come from all the three contributions. Okay, and the distance from this x means all the masses and the distance from the reference axis. Okay, and equal sum over x. Now as you see, this oxygen molecule is aligned along the z axis. Okay, so this is not far away from z axis, so distance is 0, so contribution of oxygen molecule will be 0, right? But for hydrogen, sorry, it's not molecule, hydrogen and oxygen atom, the contribution of oxygen atom will be 0 because the distance of this oxygen atom from the reference axis is 0. So if the distance is 0, then its contribution to the moment of inertia along that axis will be 0, right? But for hydrogen atom, you see it is separated by some distance from the reference axis. Okay, so for this case their contribution will be non-zero, right? And we have taken this axis to be x-axis, so perpendicular to this will be y-axis, right? So this is nothing but, then there are two masses. Let's say each mass has some, each more atom has some mass m. Okay, let's say this is mass of hydrogen and the distance they are being separated is ROH sin theta over 2. Right, and there are two such atoms, so I can simply multiply 2. Right, so this will give me the moment of inertia. Right, are you getting?
It will be RO is sin theta by 2 square.
Oh yeah, sorry, yeah, this whole square. Okay, thank you. Right, so this is 2 times mh times ROH sin theta over 2 whole square. Right, so this will give me moment of inertia. Okay, now what else is given? The rotational constant A tilde is given. Now previously I have, in previous questions, we have calculated the moment of inertia in terms of, yeah, you see here, okay, notations are different, so you can calculate moment of inertia from the rotational constant. Right? Here B tilde is rotational constant, and in that question it is given A tilde. Okay, we can use this formula and we can calculate moment of inertia. Right, then we have already moment of inertia form. So, okay, IZZ I can write it to be h cross over 4 pi. Okay, for this question the notation is A tilde C. Okay, we have some other form, h cross over 4 pi A tilde C, and we already know IZZ to be of this value, and this A tilde value is already given. It's 14.512 centimeter inverse. Now what we can do, we can equate these two equations. Right, so let me calculate this quickly. So this will give me h cross over 4 pi A tilde C equal to 2 mh ROH and theta over 2 whole square. So you know h cross is known, 4 pi you know, A tilde is given, C is speed of velocity you know, mass of hydrogen you know. What is unknown here is ROH, theta also you know. So if you do this, if you solve this, okay, then ROH sin theta over 2 will be h cross over 8 pi A tilde C mh, or ROH will be h cross over 8 pi A tilde C mh times 1 over sin theta over 2. Right, so you got the formula to calculate the bond length between ROH. Right, so every value you know, you just put it, then you will get this value to be, just to verify it, okay, 9.6024 times 10 to the power 11 meter, or 0.96024 Armstrong. Okay, so you are given a triatomic molecule, like water is given, water molecule is given, and the rotational constant around z axis is given, and the bond angle is also given. So with this limited information, what we did, we calculated the bond length between oxygen and hydrogen. Right, so any doubt from this question?
it's okay, sir.
Okay. Okay. Okay, moving on to the next question. Okay, calculate the bond force constant K for HCl molecule, and the fundamental frequency is given as 2990.9 centimeter Hg. So we are considering vibrational frequency. So the assumption is this system is harmonic oscillator. Okay, and then the energy form will be n plus half h cross omega, or in terms of transition length, we can replace this h cross omega by nu e tilde. Then this will, let's denote this energy to be f tilde n plus half nu e tilde e. Okay, so this nu e tilde is transition line is given. Now what you have to do, you have to calculate this K. So for the case of vibrational spectroscopy, what we assume this system to be approximately equal to harmonic oscillator. Okay, so in that case, what happens, the potential energy will be half times some constant K times the displacement square, where this K is the bond force constant, right? So we need to calculate this K value from this question. Okay, now what is given, the molecule is given to be HCl. Now you know the molecule, then what you can do, you can calculate the reduced mass. It will be mass of hydrogen and mass of chlorine divided by mass of hydrogen plus mass of chlorine. So approximately I can take this MH to be 1, times 35 by 1 plus 35 atomic mass unit. Okay, so we have 35 over 36 AMU. Now you can always convert this atomic mass unit in terms of kg. So you have to multiply a factor 1.661 times 10 to the power minus 27 kg atomic mass unit inverse. So if you do this, you will get this value to be nearly 35. You will get this value nearly 1.614 times 10 to the power minus 27 kg. So you have mu. Now the fundamental frequency is given. Okay, Now then, uh, from the previous class, if you remember, this fundamental frequency we can write in terms of force constant and effective mass as 1 over 2 pi c times k over mu half. Okay. Or if you know harmonic oscillator pretty well, then you know this relation omega is root over of k over m, right? This is force constant, m is the mass of the particle, then the fundamental the rotational frequency can be written as root over of k over m. So similar to that, this omega is not even 2 pi mu, and this is the frequency. We can write this mu in terms of wave number by simply multiplying by c. So this will be converted as in terms of wave number, and for this system our mass is reduced mass, right? So from this we can get this relation mu bar to be 1 over 2 pi c times k over mu. At this k is given in terms of wave number. So from this we know mu value, right? We calculated here, and this value we know. From then, what is the unknown? K is the unknown. So we can calculate k. So k over mu will be 2 pi c mu bar whole square. Then k will be 2 pi c mu bar whole square times mu. Okay, so every constant value we know, 2 times 3.14 times 3 into 10 per 8, and nu bar is given in terms of centimeter inverse, right? Now we can convert it to meter. So it's 2290 times 0.9 10 per 2 meter inverse. This whole square, and mass we already got 1.614 10 to the power minus 27 kg, right? So if we solve this, we will get value. So let me do this. This is 43182.44 small square times 1.614 times 1. Okay, so this will give me 3 10 to the power 29 times 10 to the power minus 27 Newton meter inverse. This is 300 Newton meter inverse. Okay, so what was given in the question? the fundamental frequency was given. So from this form you can easily identify this is the wave number. Okay, and the molecule is given HCl, right? And as we are considering vibrational motion, so we can approximate this system to be nearly equal to harmonic oscillation. Okay, so if we consider this to be harmonic oscillation, then the potential energy is equal to half kx square, where this k is force constant. Okay, and the vibrational frequency, the rotational vibration frequency for this case can be written as k over m root over, and we can always convert this rotational frequency to linear frequency, and linear frequency we can convert to wave number. So from this we got this relation. Okay, as the molecule is given, we can always calculate its reduced mass to be this much. Now we have value of mu, we know this nu bar, then we can easily calculate the force constant. Okay, then moving on to the next question. Given that value of B is 5800 megahertz and nu tilde is given this much for carbon monoxide, calculate the frequencies of the first few lines for R and P branches in the vibrational spectrum for carbon monoxide molecule. Okay, so if you remember, in the initial classes we learned about the branches, R and P branches. There was some distribution like this, and these distribution lines like okay. So if you remember from the earlier classes, so these lines were defining the transition lines. Okay, so this line is defining the transition from 0 to 1. This line defines 1 to 2, 2 to 3, 3 to 4, and so on. And on the left side, this defines 1 to 0 transition, 2 to 1 transition, 3 to 2 transition, and so on. So this middle line, this we call as Q branch, the Q branch, and the lines towards right we call as R branch, and the lines on the left side we call as P branch. Okay, so what these lines represent? This line represents the transition with delta J equal to plus or minus 1. So the right hand side delta J is plus 1 and for the left hand side the delta J is minus 1. Okay, so we need to calculate the frequencies of the few lines towards R branch and P branch. Okay, so if I consider the R branch side first, then the transition line towards R branch I can write in terms of this ground state, what do you call this, ground state line, let's say. Then this transition towards right we can write as 2, so this is literal 2b tilde times j plus 1. Okay, so this is your reference line, let's say new bar, and you are going delta j equal to plus 1, right? Okay, then this is new r, let's say. Then we know the difference between adjacent lines, this will be 2 beta tilde j plus 1, right? Now as we are considering delta j to be plus 1, so this will be added to this new bar. Okay, now we have new tilde 2160 centimeter inverse plus, now it's given in terms of hertz. So what we can do, we have to convert it in terms of this same unit, right, centimeter inverse. So what we have to do, we have to, so this is frequency, right, 1 over time, 1 over time unit or 1 over second unit. Well, we need to convert it to centimeter inverse. So what we can do, if we multiply speed of light in the denominator, then this will give me meter per second. Okay, let's just do this. B tilde is given 58000 megahertz, so it's megahertz means second inverse, so I can always convert this to length inverse by dividing speed of light. 0 megahertz is 10 to the power 6 hertz means second inverse. If I divide speed of light in this, then this will give me 3 into 10 to the power 8 meter per second, or this will give me 558 divided by 3 times 10, it's meter inverse. Then this will be 160 meter inverse. Now we have to convert it to second inverse, centimeter inverse. So this will give me 160 times 10 to the power 2 centimeter inverse, right? Okay, 1.6 centimeter inverse. B tilde we got in terms of centimeter inverse, so this will be 2 times 1.6 times J plus 1, right? Now this will be 2160 plus 3.2 plus 1. Okay, so J value we don't know, so we will keep it as it is. So this is 2160 plus 3.2 and J plus 1. What is the unit? Centimeter inverse. So this much okay, this is the frequency to do the transition towards R branch. Okay, so now if we consider P branch, what will happen? This will be simply minus, right? Or minus 2b tilde J plus 1, because it's this transition is weak, having towards left hand side. So the fundamental frequency, from the fundamental frequency, this line will be deducted. So this will give me 2160 minus 3.2 J plus 1. Okay. So this new bar is, or new tilde was given to be this much value, and the system is carbon monoxide. Then what we are asked to calculate the lines towards left and right, or R branch and P branch vibration and rotational spectrum. Okay, so the vibration contribution is pretty small, so effectively we can write it in terms of rotational correction. Okay, so if R branch is considered, so this frequency will be added. If P branch is considered, this frequency will be deducted. Okay, now moving on to the next question. A simple function that is a good representation of internuclear potential is the most potential. So this potential is given in this form, where this Q is R minus RE. So this is length, so that the force constant calculated for the most potential is given by 2 dE beta square, and dE value is given and beta value is given. Then we have to calculate this force constant K. Okay, so this internuclear potential is given as this U Q is given dE times 1 minus e to the power minus beta Q square. This is length unit. Okay, so this potential is given. Now we know for a good approximation we can approximate this potential to be like simple harmonic potential. So for that, let's do one thing. Let's expand this e to the minus beta q. So this is minus 1 minus. If I expand this e to the minus beta q, this will give me 1 minus beta q beta square q square 2 and higher order term. Okay, whole square. So if I solve this will give me dE beta q plus beta square q square 2 plus higher order term. Okay. Okay, so it's whole square. Right. Now if I do the square, so what I'll have dE times, there are several terms, right? So it's like a plus b plus c plus whole square. So let's take up to these two parameters. Let's take up to this second order term. Then if I do the square, what will happen? This will give me b square q square plus some order of beta cube, that means cross term of these two, then order of beta 4 and so on. Okay, so as beta is so small, we can okay, not beta, as the length is very small, we can approximate up to this first term, and then this will give me dE b square q square, right? So this potential I can write approximately to be this dE b square q square. And if I assume like we know at the bottom of the potential, like if this is the potential, at the bottom of the potential we can assume this potential to be always harmonic. So in that case the potential will be half k q square, right? This q is the displacement length unit. Okay, so if I equate this to half k q square, then from this what I will get? I can get k value, right? Q square will be cancelled, then k value will be 2 dE b square, right? So the exact potential can be given by this Morse potential. So around this minima, this RE, we can always approximate this potential to be simple harmonic potential, right? So if some small oscillation is happening, then in that case the potential we can write as half k q square. Okay, so what we did, we approximated this potential to simple harmonic potential. That means we equated this potential, then from this equation we got the value of k to be 2 dE b square. So we were asked to show that this k value to be 2 dE beta square. Okay, now dE value is given and beta value is given, then we can calculate k value, right? So dE value D value is given to be 7.31 10 to the power minus 19 joule per molecule, and beta value is given 1.83 per 10 meter. Right, then it's pretty straightforward. K will be this dE square, sorry, dE, okay, let me write, K will be 7.31 times 10 to the power minus 19 times beta is 1.83 times 10 to the power 10. Then okay, 2 is there, 2 times this one, so this will give me 490 Newton per meter. Okay, this is the force constant. If I put all this value, I'll get the force constant value to be 190 Newton per second per meter. Okay, then moving on to the next question. Okay, the Morse potential is presented in the above problem. Then D is given this much, and nu E bar is also given, and Re is given for oxygen molecule. Then plot the Morse potential for oxygen molecule and also plot the corresponding harmonic oscillator potential on the same graph. Okay, what is given? This transition line nu E bar nu tilde is given to be 1580 centimeter inverse. Okay, now few questions back we had a relation nu E tilde to be 1 over 2 pi c times k over mu root over. Okay, so from this relation I can get the force constant, right? So this will be nothing but 2 pi c nu E bar whole square mu. Okay, so as the molecule is oxygen, so the reduced mass will be 16 times 16, 16 plus 16 is 2 into 16, so it's near to 8. Okay, atomic mass unit. Now if you put all the values, you will get this k value to be nearly 1176.3 Newton per meter. Okay, so nu E tilde was given, from that we got k value. Okay, so if you got k value, then what we can do, so what was the equation? This was the equation. We got the k value and d value is given. The only unknown is beta, right? We need to plot this, okay, this potential, so we need to know all the parameters, and q is the variable here, so we need to plot this potential with respect to q. Q is nothing but the distance. Okay, so beta value we can calculate from this relation. We got already k value, and beta value we can calculate from this relation. So beta will be, so we had k equal to 2 dE beta square, right? So then from this we can calculate beta to be k over 2 dE root over. So if you put all the values, you will get 2.83 times 10 to the power 10. right? Ten to the power 10 Newton per meter. No, sorry, this is beta, this is not K, meter. Okay, so you got beta value, you got K value. So we have two potentials now. One is dE times dE times 1 minus e to the power minus beta q whole square, and another potential, let's denote it by B. This will be half K q square, right? Now every constant value is given already. Now what we have to do, we have to plot these things, right? So you have all so I encourage you use some software and you have all the values already. Then if you plot these potentials, I am showing the nature of this potential. So if you plot this u, will get the potential to be, so it will be steeply declining, then it will go like this. So this is u. Okay, now if you plot this potential v, let me denote it by dashed line. So this will be like this. Okay, so this is harmonic oscillator potential, and this is Morse potential. Okay, so I encourage you do the plotting using some software. Okay, so if you plot these two potentials, you will get this one. Okay, so you just try it. As today it's already time, we'll stop here and we'll meet